because we have really very interesting stuff ahead of us, and particularly the cosmology part of this course. So I want to kind of proceed through these more or less technical overview type of lectures in a reasonable amount of time, not spending too much time on it. So the next topic is the deep sky surveys. And that answers the question, how do we know all that structure? Sorry. Full screen and my pen pointer. So I'll talk about the different types of surveys that have been done basically since roughly the start of the millennium, maybe some started earlier already, but and are ongoing major investments and in money and in material, in instrumentation and in time, huge international corporations. We'll talk a little bit about the type of instrumentation they are using for that. And we'll come back to the concept of dark matter, which continues to haunt us till the edge of the universe. Because we've seen it at the local scale, local in the sense of our own galaxy, motions of the stars in the outer regions of the galaxy. And this will continue to be the problem to observe or to explain into the deep universe. So we need to come back to that a little bit. And then I'll talk a little bit about how computer simulations are very important in studying this large-scale structure as well. Okay. They call them redshift surveys because redshift is a measure for distance. We will talk about that in detail later because that's in the cosmology part. The point is that we cannot simply talk about distance anymore if the universe is expanding as it is. So we need to redefine these concepts. And redshift in the deep universe has a completely different physical origin than the redshift based on the Doppler principle in the nearby universe. With redshift, we talk about spectral lines that we observe, and they are not at the wavelengths where they should be in the laboratory, like hydrogen alpha, for instance, the red hydrogen line. We know what that wavelength is, but they are shifted towards, in particular towards the red, towards the longer wavelengths. And that's because things are moving away from us. But redshift in the cosmological sense is a different kettle of fish. That's not a Doppler effect, and I'll talk about that. But this is the reason why they call those surveys redshift surveys. The general way in which they display results is in these wedge form, where the angular measure is basically a direction in space. They have some scale here, right ascension or declination. This is right ascension here if it's in time units. And the radius is the redshift. That's the distance, essentially. And then you can easily see here in these examples that this is the type of structure that they will find. These are wedges that they observe in different campaigns. They cannot observe in all directions at the same time. So they choose certain regions which they can scan with the instrumentation that I'll talk about. And then they get to this kind of result. The very earliest surveys were in the 1920s. Shapley, again, he was very active in observing galaxies, redshift, those kinds of things. The first systematic survey, what in the context of what we talk about now, was already in 1976. I said it started in the beginning of the millennium, but then it really took off. But this is an early example. It's called the famous Lick catalog. Lick is the name of an observatory. This is a representation, an all-sky image. They wouldn't have been able to measure distances at all. This basically was based on a count of galaxies. The Center for Astrophysics, CFA, in Massachusetts, has been very active. These are called the CFA surveys. These are some early results. 82, probably both roughly that same age. And here you see examples of such a wedge representation. So this is the direction in space coordinates, and the radius is basically here it's expressed as kilometers per second, but that's a velocity. But that's basically the radial velocity that they calculate from the redshift. But that's a measure that we don't use anymore because we now use a concept called cosmological redshift. I'll talk about it later. But here they have identified 249 galaxies. This is another slice. Became very famous because they called it the stickman figure. The slice with the stickman figure really looks like it. This is just some early structure that they discovered in these surveys. The second one, yeah, I was wrong in saying that it started in 2000. It started in the 1980s with these kinds of surveys. This is a much more detailed one, almost 6,000 galaxies identified in one slice in a systematic survey. And here you see the structure that they discovered. I want to show you the interview with this lady here, Margaret Geller. She was a very instrumental astrophysicist, astronomer in those days of observing structure of galaxies. So I need to share, and hopefully I'll do it properly now. Go to the next lecture folder. Again, the surveys. How to find the galaxy, Margaret Geller. Very nice lady. She's retired now, but she was very active.
This story is as big as it gets.
It's really the longest journey a human being can take.
It's a journey to the outer reaches of the universe. And here's the question. How are the tens of billions of galaxies inside this universe of ours distributed? Are they scattered randomly, or is there some kind of pattern? Margaret Geller began her quest to map the universe in the 1970s.
We were limited to using a very small telescope, and it was a slow process, 25 minutes a galaxy.
25 minutes to determine each galaxy's 3D position. The latitude and longitude are easy. They come from the image that the telescope takes.
But galaxies don't come with little tags saying how far away they are.
And so what's an astrophysicist to do but get clever by measuring something called the redshift?
And we do that by spreading the light of a galaxy out into its colors. Then we can see features that tell us how rapidly it appears to move away from us.
The faster a galaxy's moving away, the more we see its light getting stretched towards longer wavelengths, and the larger the redshift.
That's proportional to the distance, so that's how we know how far away a galaxy is.
Now, Geller couldn't survey the entire sky. It's the classic too much universe, too little time problem.
Let's suppose you were going to see the Earth for the first time, and you wanted to know, does it have continents and oceans? Well, if you take a small patch, it won't tell you anything. But if you take a great circle in almost any orientation, it'll pass through continents and oceans, and it'll tell you the Earth has two kinds of structures, both big. In the universe, of course, it's a 3D place. So the analogy is you take an orange and you cut a slice in it. So we observed galaxies in a slice of the universe.
And it worked. She and her colleagues plotted the locations of 1,000 different galaxies up to 700 million light years away.
When we saw the data, there was this glorious pattern. The galaxies are all in very thin structures which surround or nearly surround vast dark regions where there are very few, if any, galaxies. And it was known that there were clusters of galaxies, but what wasn't known was what was the general structure of the universe. This was the first time you could really see it patterns that extend for hundreds of millions of light years.
In her subsequent maps, like this one, that went way deeper and contained tens of thousands of galaxies, the pattern held. Margaret Geller and her two colleagues had found the continents and oceans of our universe.
For that moment, you're the only three that know it. That's it. Of the billions of people in the world, it's yours. And so for that moment, you own the universe.
And then Geller gave the universe to the world, helping reshape not just our understanding of how matter's distributed in space, but also how that matter got there. You see, there's a kind of faint radiation that fills outer space called cosmic microwave background. It's a remnant of the early universe.
That radiation has little tiny ripples in it.
Ripples in temperature.
Some regions are just a little bit hotter or just a little bit cooler than others.
And those differences in temperature are related to differences in the density of matter of the early universe.
So what happens is that gravity amplifies these ripples in the matter distribution. And so in an expanding universe, two things happen. Gravity likes to make lumps. And it also turns out that gravity likes to make holes. If you start a hole, gravity will make the hole bigger. And that makes the structure that we observe today.
On cosmic scales, it's all about gravity. But on human-sized scales, for Margaret Geller, it's about something else.
The journeys that we take in science are journeys of the imagination. It's a measure of our curiosity and our reach. It's what makes us grand, in my opinion.
A very wise woman, I think. So she was one of the earliest pioneers in doing these sky surveys. Or did she say 20 minutes for one galaxy? That has become much faster. I'll show you that in terms of the instrumentation. But this is, I think, a very good introduction into the history of how this came about, these large-scale surveys. This is the 2-degree field galactic redshift surveys, what's called. The Anglo-Australian telescope was used. This was around the turn of the millennium. Here's an example of it, and this is an animated rotation of the slice. This is all they can do. They cannot do all sky surveys in this way with this technique. They need to define a slice of interest, and then, like Margaret said, a slice of an orange, and that's what you study in detail. We will get back to the full sky surveys, and that's a technology that's coming up and partially already here. I'll come back to that. This is the 6-degree field. There's an all sky kind of representation here with the zone of avoidance because of the Milky Way disk. So this is already more than 100,000 galaxies. Just imagine that you would have to spend 25 or half an hour on one galaxy. You would never get finished. These are more recent in 2013 kind of surveys called Deep 2 and Deep 3. They use the Keck telescopes in Hawaii on the Mauna Kea ridge of the volcano ridge. And they have different scientific purposes, those surveys. It's not just to make pictures of the structure, but for instance, studying galactic evolution is a very important topic. The deeper you look into the universe, the older the stuff is. I discussed that last week. And that means that you can kind of get an impression about the history, the evolution of galaxies from the very early stage in the deep space to the more recent types of galaxies which you find in the nearby universe. This is how we make advantage of the fact that we look back in history by definition. Discussed that last week. I'm not going to go into too much detail here. This is a famous strip. Again, this is just one particular area in the sky where they have combined different projects that have been happening, different surveys that have been happening. You see the HST here, the Hubble Space Telescope, is also included in here. This is how they can try to combine the efforts. And this is a multi-year effort in international context. So this is really a slow, but very high intensity kind of projects that they perform. And I'll come back to that here. This is the Sloan, arguably the most famous one, started in the early 2000s. And that's still ongoing. That's what I was going to say. It's still ongoing. We're not finished. We never finished, probably. And the instrumentation gets better, of course, as well. So here you see a sequence of various campaigns in the Sloan Digital Sky Survey. Sloan is, I believe, the name of a legacy of a rich family in the United States. They have left a fund behind, and that must be a lot of money. And that's funding this ongoing, all these surveys, which started in the early 2000s. They use the main telescope, and how it started is the Apache telescope, or Apache Point Observatory, I should say, in New Mexico. They also have a southern component now since SES-4, since campaign number 4. They use, in addition, the Las Campanas observatory in Chile. Because if you're in the northern hemisphere, of course, you can only see half of the sky, basically. So here you have this Sloan Great Wall I was talking about. But here you have the actual way in which they identified it in one of these slices, this particular linear structure that was referred to as the Sloan Great Wall. And it's named after that survey, as you can understand now. It's a distance of about 1 billion light years, and the total length of it, I don't know how they define the total length. That is something like 1.5 billion light years. Another result of one of the SDS campaigns. You see here clearly the redshift that they indicate now, and it is a measure of distance, but I'll explain this. I'll just give you an indication here of the scale. This 0.14 in terms of redshift relates to a travel time distance of 1.8 billion light years, which means that the light from these objects, this distance, has been traveling for 1.8 billion years. That's really what it means. And again, I'll come back to that, because the cosmological redshift and also the fact that you need to define distance in an expanding universe is going to be a major topic in the next, further on in this course. But this is just to give you an indication of the distances that we talk about here. This is a fly-through. I'm hesitating if I want to take you there. Let me do part of this. Because I want to show you two things. One is the fact that we can identify this structure based on observations. So this is what it is. What you see here are all galaxies, and we are flying through. But this is not just artistry. These are actual locations defined in the computer based on the observations. So this whole structure, this whole collection that you're flying through here is actually real. But the other thing I want to mention is that there's no way that you can do this in reality, no matter what kind of spaceship you would have. Because the speed with which we are moving through this collection is probably millions of times the speed of light. If we would travel at a human space as a velocity, or like real spacecraft, if we ever get to that point, to that distance, then it would be an extremely boring video. You would have to study this for years to see something move. So that's a word of caution. But this is the structure that we can put in computers based on observations. So this is an actual three-dimensional representation. So let's leave that for that. This is the latest. It is planned to run to next year. This is the S5, Sloan Digital Sky Survey number 5. This is just an infographic about which telescopes are involved and what the type of applications are. I'm not going into detail here, but you can always go back to the handout and you will find more details. This is another, there are different sub-programs because of the various scientific goals for each of these surveys. And the SDS S5 has a collection of different study objectives. EBOS is one of them. Comes from baryonic oscillation or something. It's something I won't even talk about in the cosmology. I'll probably mention it briefly, but this is really a study of deep space universe, and it's related to cosmology. I will show you this interview because it is really interesting to give you an idea about how these people are working on those kinds of surveys. So let me share this video with you. As the SS largest 3D map of the universe, it's called.
So EBOS is a collaboration of about 100 or so people. They're distributed all over the world. There's about at least 10 different countries with participating members. And in particular, we have people in New Mexico who really run the experiment day to day, and they really put in an enormous amount of work making this a successful experiment.
Within cosmology, we have a standard model. This model describes how, on the largest scales we can see, the universe evolves. So EBOS is designed to measure the three-dimensional positions of galaxies. One of the techniques we use with EBOS data to measure the expansion of the universe is called the baryon acoustic oscillation technique. This uses a standard ruler in the distribution of galaxies. And we use this scale to measure the accelerated expansion of the universe. It is considered an incredibly robust technique within the community.
When the light of the distant galaxy propagates through space, it is stretched by the expansion of the universe, which changes wavelengths and makes it redder, and this is known as the redshift. So the further the galaxy is, the greater the redshift will be, and that allows us to infer its distance. However, the redshift has an additional component that is due to the small contribution of the galaxy's own velocity, and which moves in response to the gravitational attraction of the surrounding matter. And these two components cannot be really separated from each other. But the statistical analysis of the data from the EBOS allow us to distinguish these effects of the velocity from that of expansion.
The biggest challenge of EBOS, the sheer size of the project. There's machinery with many, many moving parts, and those parts are being run all over the world, is when we're actually running observations week after week, year after year, for 5 years, observing over 1,000 independent fields. We have to make sure that's all done uniformly and consistently in a way that we understand the entire throughput of this system. You have many analyses going on, projects, analyses being done in different countries, being done by different people, and you have to have this network where everyone is in agreement about how to proceed to the final measurement and make sure that everything is understood at better than the 1% level.
That allow us to accurately reconstruct the history of the expansion and the growth structure of the universe over a cosmic time time of about 11 billion years and covering almost 80% of the entire age of the universe.
So it's really exciting times. We're pushing to galaxies that are further away from us than has previously been looked at. And we find that even for these galaxies, this standard picture holds.
The SDSS has had a huge impact over the last decade on measurements of the curvature of the universe and its current expansion, represented by the Hubble constant. We've been able to significantly shrink the allowable parameters with regards to the curvature of space. Thanks to eBOS, our best constraints show that it is nearly flat, with 70% of the current energy density in the form of dark energy, a mysterious component that is causing the current acceleration.
I'll stop here. This is all cosmological speak, and it will become a lot clearer, hopefully, when we proceed through this course. So this clearly is primarily this program, eBOS, is primarily aimed at cosmological questions and scientific objectives. But I found it interesting for you. I thought it was interesting to see those people who are running these campaigns, how they are basically how they are working and how they feel about what they're doing. You can help yourself. This is such an enormous amount of data that comes out of these surveys. They still have a lot of images that they would like people, and people like you and me can participate if you want. Go to that link here, the Galaxy Zoo, which is a general organization now who enlists basically citizens, anyone who's interested, students, doesn't matter. If you have some time, you can get different topics. If you can choose different sections of the work that they have. One example is you can get a selection of images of deep space images, and you'll be asked to identify a certain type of galaxies and just label them, indicate them, something like that. So you can anyone can really help. This is an enormous amount of work. It will never stop. It will only get worse because of the new instrumentation that's coming along. Yeah, there are many more. I have a full list, I think, in the handout. That's probably on your Wikipedia, a list of all the surveys, deep sky surveys. Let's talk a little bit about the instrumentation that they're using, because this Margaret Geller, she talked about 25 minutes per galaxy. That's absolutely undoable if you talk about hundreds of thousands of them. So we must find other ways to make it more palatable. Here's an example. This was in the early days still, 6-degree field. You see here a circular plate. It's a metal plate. This will be mounted in the focal plane of the telescope when it's ready. But this is a robotic machine, a robot, that's put these little prisms connected with a fiber, an optical fiber, and it's a magnetic plate, or there's a little magnet in here. It's a metal plate. This robot is put these little prisms at a precise location in this plate, which means in the focal plane of the telescope later. That means that it will be pointed at a predicted position of a particular galaxy. And they had 150 of these prisms on one plate. And that's how they could observe 150 galaxies simultaneously. And each fiber went to its own spectrograph. But they got 150 spectra in parallel from one observation. So that really was the way to start speeding up this whole process. These are the telescopes I talked about. Then they had, in the Sloan survey, they first had metal plates where they drilled holes, and somebody had to connect fibers that were color-coded to these different locations. The same principle, but here it's just a fiber directly plugged into a plate. And now they have robots themselves who are putting these fibers automatically in predefined positions. But now the loading time for a whole observation of a night, which involves hundreds of galaxies, can be loaded in 2 minutes. In the video before, you saw them working with the Sloan Digital Survey with this thing, and they were loading units in the telescope. I don't know if you recall that that was part of in that video, not the last one, but the one before. That is how they load these plates into that telescope, into the focal plane of that telescope. These plates are during the daytime. They have prepared all of them for the night observations, and then they just roll them out. But it's still a lot of handwork. But now they can observe 500 galaxies basically at the same time in parallel, and they can up to 9 plates, 9 of these sessions in one night, in one successful night. So this is how they speed up the process of observation. And then we have the Vera Rubin Observatory, as I mentioned before. This will come online hopefully next year. This is going to be a complete change of the astronomical world. You will hear about this from decades to come. This is a survey telescope, which means it's wide angle. All these telescopes I've talked about, they are wide angle. That's what they mean, the survey telescope. A large field of view. This one has the largest digital camera connected. And it will survey this is in Chile, so it will be partially the southern hemisphere. Survey as much as it can in one night, and only in a few nights, in 3 days or 3 nights, it will have covered the entire hemisphere. And then it will repeat. And this is what it will be going to do systematically for years. The amount of data that's coming out of this is unbelievable. They need a special data connections to computing centers to get rid of all the data in time, because the telescope will continuously survey. The purpose of this observatory is not just deep sky. It does anything that moves, basically, even asteroids that could come too close to Earth. Basically what it does is feeding the images from the camera into computers. Computers analyze, they stack the images of the same part of the sky and see if anything has moved, anything has changed. That's essentially what it does. And if anything has moved, it generates an alert. That's how they work together. Anyway, between observatories, you can have an email subscription on a particular type of alert for a particular observatory. If you're interested in supernova explosions, for instance, that you're among the first ones to know, hey, there's this happening right now. But this telescope is going to produce something like 1 million alerts every single night. It goes in all kinds of different directions because it's based on different astronomical phenomena, including deep space and very much dark matter survey, or dark matter study rather, based on motion that we observe. That's why it's called Vera Rubin, because Vera Rubin is the one who basically, as I discussed last term, discovered the velocities of stars in the outer regions of galaxies, and this rotation curve problem, which can only be explained with some gravitating matter that we cannot see, but we see it, we notice it's there because of the dynamics. So that's That's a major component of the survey, but it will observe anything in the sky that moves. It's absolutely, it will completely flood the astronomical community. Okay, so that's coming up next year. This was launched last year, yeah, 23. The Chinese Survey Telescope, again, wide field survey telescope. And the Purple Mountain Observatory. Very similar purpose, from nearby solar system objects to deep space galaxy clusters. So these are the modern applications, additions to those surveys that have been going on and that are still going on in some ways. The Hubble telescope it's a multi-purpose telescope, been around now for more than 30 years, but it's still, but it is multifunctional. It is for the scientific, there are several scientific objectives for which it has been launched and it's being used. One of them is the Hubble Deep Field, very famous observations. Somebody came with that idea. This was not originally planned for the Hubble, but somebody said, let's point it, and this was in the Northern Hemisphere, let's point it in a dark piece of the sky. The Hubble is not a survey telescope, it has a narrow field of view. Let's point it at a dark patch of the sky where we don't see stars, and let's just let it integrate with a very long exposure time, and let's see if it comes up with something. This is the reason why they came with these extremely interesting deep field observations, because these are all galaxies that are probably billions of light years away. That's why it's called deep field. They were amazed that there was nothing to be seen visually through a telescope in that direction. But if Hubble stared long enough, it could produce these kinds of deep sky images. That just has been repeated in many, many forms because it was such a successful thing. You can watch this summary here yourself. There also has been a southern version of it now. And then, of course, we now have the James Webb Space Telescope, which also, it's not a survey telescope. It has a relatively narrow field of view compared with the wide field telescope, but it can peek deeper into the universe because it has a higher sensitivity and also much better resolution than the Hubble. And again, this is a multi-purpose telescope, but one of them is the deep field studies. And this was one of the first, this was the first deep field observation produced. I think I have showed you this last term as well. I'm not sure. Otherwise, we'll come back to it. But, and I will come back to the James Webb Telescope. It has a whole array of micro shutters. And it's absolutely, the technology is absolutely amazing how that works. But they can open and close shutters magnetically, and these are micro. They're a few times the width of a human hair or something like that. So the whole field of view is divided in a whole matrix of cells, and they can open or close any of the cells. And if they know that there's an object in the field of view in a particular location, they open a cell, and that cell is being connected to a particular part of the spectrograph. And here you have a slice, and in this little square here, they had opened a cell, and this is the larger version of it. And this is a galaxy. The light that we see now has been traveling for more than 13 billion years. But this was immediately a record of how deep the James Webb Telescope could see. And the amazing story behind it is that the James Webb Telescope could produce a spectrum of that galaxy. When we talked about spectroscopy, that was in term 2 this year, I mentioned how powerful that technique is, because as long as distance really doesn't matter. As long as you receive photons, you can produce a spectrum. And that's what James Webb has shown here. So this is not survey in a particular sense, but it is going really very deep into the universe. And the James Webb is the deepest, goes the deepest now as the Volta telescope. And I'll come back to that later in this course. Some of the results. Euclid is a European telescope that's not a survey telescope as well either, but it has a similar scientific purpose as the Vera Rubin Observatory. It's this distribution of galaxies, studying galaxy evolution, galaxy clusters, etc. And because this is in outer space, in orbit around the Earth, it will continuously observe, and this is expected to give also an enormous amount of extra data. And then the NASA is working on the Nancy Grace Roman telescope, also a space telescope, infrared, I believe. Also has cosmological, primarily cosmological purposes. I'm showing you this because you can expect in the next decades that there is dramatically new information coming around. It's a really exciting time to be alive now. Okay, let's go back to the dark matter issue. This is Vera Rubin, and I talked about this in the Milky Way course as well, because she produced these rotation curves, as they're called. This is the distance from the center of the galaxy. This is the rotational velocity in kilometers per second of any particular stars. Here you see the spectrographic way that she studies other galaxies, because this is not only the Milky Way, this is not only our Milky Way, these are other galaxies. In the field of view, you set up a slice, an aperture, in this case across an entire galaxy, and then you look at you feed the various parts of this slice into a spectrograph. You see the shift of the spectral lines, and here you can see very systematic that this galaxy is rotating, because in one part it's red shifted, means that this part of the galaxy is moving away from us, and this part of blue shifted, that means that this part is coming towards us. So this is how she measures rotation. And if you go further away, the rotational velocity stays more or less the same, whereas we would expect with normal gravity that it would tee off like this. I discussed this last course, so I'm just reminding you of this. And so this is the discovery basically of something that we don't understand, but it has a gravitational effect. We call it dark matter. And this is an ongoing discussion in astronomy, and especially also in deep space observations where we are now. This is something that, as I mentioned before, it kind of haunts us. We can't get away from it. It's actually getting worse. This is an example of, well, the gravitational lensing is this principle that we are observing in the foreground, which is very far away, but we call it foreground. There's a galaxy cluster, which is basically a collection of mass, of matter. And behind it, in our line of sight, there's an accidental occurrence, of course. There may be a galaxy or another cluster of galaxies much further away. And because of the gravitational lensing effect, the bending of light because of gravity, because of the matter energy density collection in this cluster. This is what I discussed last term when we talked about general relativity. We can see this distant object in different ways. So we can see ring-shaped structures, and wherever we look, we see this. Initially, these were called Einstein rings because, of course, it relates to the general theory of relativity. Anyway, In this way, we can study the amount of bending that happens, and which gives us an estimate of the total amount of matter in that foreground cluster. And we always see that that the visible amount of material that we see is only a small fraction of the mass, which is actually there, which must be there because of the bending effect. This is a famous example of another Abel object. It's a galaxy cluster where the visible light contribution to that amount of mass that we can calculate is only a fraction. So these are dark matter studies that are ongoing. And here's another very famous example of a so-called bullet cluster, which is a collision or a merger of two galaxies are going through each other at very high velocity. It's still very much in discussion, but this is one interpretation. We can observe in different frequencies of electromagnetic light. We can observe densities, that's the color coding here. But if we look at the lensing effect, we can reconstruct that there must be an amount of gravitating material, which we can't see, and which is indicated by these contour lines. So this suggests that there's a lot of dark matter, whatever it is, which is either lagging behind the collision or whether is running ahead. I'm not sure. You can go to the lecture, the handout, and you'll see a reference. Some people say that this is not the right interpretation. It's in discussion, but this is generally mentioned as an example of famous example of dark matter that must be there in a very large amount compared to what we can see. Okay, finally, a few words on computer simulations. So we want to reconstruct the evolution of galaxies. We can see only so much. We can observe at different distances, different stages of galactic evolution, that's the topic. And in order to test these theories, we can, because these effects, these mergers, etc., and the evolution of galaxies that takes place over billions of years timescale, in order to see if our models are more or less correct, if they make sense, is that we do a computer simulation, which is basically a video over billions of years, and see that if we let it run, that ends at a point which we actually can observe, or at different times, depending on how deep we are looking, that it reproduces what we actually see. That is the reason basically for computer simulations. You need really supercomputers for that. I have some links here where you can look at those animations. You get this kind. The computers, they produce this kind of structure, and you will remember that I've shown you images which look very similar to this kind of foam-like structure. And using supercomputers, I mean real supercomputers, the top-of-the-notch supercomputers, they can run these animations based on the law of gravity and involving billions of individual objects, and then the computer is just crunching along and making a timeline of how this evolves. And they always have to include a large percentage of dark matter. If they wouldn't do that, then it would never work. So again, very strong evidence that there is something that we call dark matter, but we don't know what it is. It has a gravitational influence. Read more in the handout of this lecture, and then we will, if you want to see more details of this. And there are some computer animations, which is fun to look at. Here, this is a collection of, we talked about super clusters of galaxies, but here you have a super cluster of computers, of supercomputers. Let me say a cluster of supercomputers, which work together so that their combined power is the same as one supercomputer running for 2,000 years. It's the kind of computer power they throw at these simulations. It's quite interesting. And of course, very costly as well. Here's an image, kind of famous. You can vaguely see here a dividing line. One of those two images is a real observation of deep space, and the other one is a computer simulation. This shows that it's almost impossible to see the difference. So they must be doing something right with those simulations. That's essentially the message here. Okay, we're doing fantastic with time. It's 9 o'clock, just past. So I've covered these two lectures. It's really an investment of billions of dollars and decades of international cooperation that gives us the results that we are talking about and that we are seeing. And as I mentioned, the coming decades are going to be extremely interesting because there are so many new projects coming along with better technology, and we will be our minds will be blown with all the results if you take an interest in this. And computer simulations are an essential tool to study evolutionary effects. So a major part of the rest of this course is dedicated to our understanding of the evolution of the universe as a whole. But now you have a bit of an idea what we mean with universe. You have traveled through it. And I've shown you a little bit about the technology that we apply to study all that structure.